All right, welcome to the last part of my video. That was a little bit of Led Zeppelin, Babe, I'm Gonna Leave You, okay, from about 1969 maybe is when that was out. Okay, so let's see, last thing we're going to look at on this section is what we call the Squeezing Theorem, and the idea kind of goes like this. All right, so if you have like three functions, okay, like this function here, h of x is the one in red, f of x is the one in kind of the light blue, and then black is the function that's literally squeezed between the other two. So if you look at this inequality, this is saying in some small neighborhood, now it doesn't have to be throughout the entire function, but if you were just kind of drawing zooming in maybe on a little piece of this, kind of like that, okay, what you find here is this function g of x, its values are always less than or equal to h of x, and at the same time they're larger than f of x. So that is literally sandwiched between those like that. So what the squeezing theorem basically says is if you have this condition, then if x approaches a, and h of x approaches L, and f of x also approaches L, then you can conclude that the function in the middle also goes to L. So it's kind of like that. So it's just basically the limit of all three of these is going to be the same at that as x approaches a. And the benefit of the squeezing theorem is sometimes it's hard to do a limit directly. And sometimes the squeezing theorem is necessary because you can find two other functions where the limit is easy to compute. And then if you find the one sandwiched in the middle, then you can compute that based on the other two functions that it's sandwiched in the middle of. Sometimes we call this the sandwich theorem too. All right. So let's see. Here's what the theorem says. So it says assume that you have three functions, f, g, and h. It satisfies this inequality. So again, this is the one in the middle. That's the one that's sandwiched between the other two. So and it's this inequality again holds for all values of x near a, not throughout the function, kind of like I was showing here. Maybe if you zoom in, there's just a little region where that holds. And then if the limit of f of x approaches L, and the limit of h of x approaches L, then you conclude that the limit of g of x also approaches L. Okay, so we're going to just do a couple of examples on this and sort of show you how this works out. So with this one, first of all, I think we're going to do a graph on this one. So on part A, I want you to just sketch a quick graph. We're going to do this on the graphing calculator. First of all, we're looking at a cosine. So one thing that you want to do here is make sure that your calculator is in radian mode. So just go mode and make sure that you highlight radian. Because if you're in degree mode, well, the cosine graph wouldn't come out the way it's supposed to. So you need to use real numbers, so be in radian mode. Okay, so the idea on this one is, let's kind of set this up like this. So first of all, let's let, by the squeezing theorem, let's let f of x be the first function, 1 minus x squared over 2. That's a quadratic function. And then let's let g of x be the cosine x. That's going to be the one that's sandwiched in the middle of the other one. And then let's let h of x equal to 1, which is just a constant function. And let's put this in our graphing calculator. So I've already got this in here. I got 1 minus x squared over 2. I've got cosine x, and then I got 1. And then I'll give you a nice viewing window to look at this thing in. Okay, so that's going to be the kind of what we have here. All right, and let's see, for a window, we're interested in the limit as x approaches 0. So we're going to just kind of find a small area around 0. So this is a good viewing window to use. And then we'll do get the graph done there. Okay, just go -2 to 2 in the x direction and -2 to 2 in the y direction. And once you get that put in, then you can type graph, and then we'll just kind of sketch ourselves a thing here. So what happens on this one is I'm going to have you just do kind of a sketch of what came out on the graphing calculator. And I'm going to put this over here to just kind of show you something here. And I'm going to label these things. So like this one was, the blue one is f of x. H of x is the black one. And then g of x is the one that's sandwiched in the middle. And what we're going to be doing is we're going to be closing in x is going to approach 0. All right, so we're going to be doing kind of a limit like that. It's pretty easy to see how this goes then. So let's see, I'm just going to go ahead and just make a real rough sketch on here. And you should do the same thing and kind of label the way the calculator is. So we're going out to 2, going out to -2, up to 2, and then down to -2 like that. Okay, so first of all, h of x is just y equals 1, so that's a constant function. So I'm going to label that as h of x equals 1. Okay, the quadratic is the one in blue. You can kind of see from the graphing calculator, it looks like, kind of goes here. It looks like it has a x-intercept around 1.5 and another one around -1.5, and just kind of sketch this in like that. Okay, so that's going to label as f of x equals 1 minus x squared over 2. And then the one in red is the cosine, and that's the cosine graph is going to kind of do something sort of like this. Okay, all right, so that is g of x is equal cosine x. Okay, so the idea is I've already given this to you. Okay, that can be mathematically demonstrated that inequality holds. So what we do on this is this. The way you apply the squeezing theorem is you do this like this, okay, when we do this limit. So the first thing you want to do is you want to do the limit as x goes to 0 of these two functions. You really want to do these limits of those two functions and see what happens. So we're going to do the limit of 1 minus x squared over 2. X approaches 0. That's a quadratic function. It's polynomial, so all you got to do is plug the 0 in. So you get 1 minus 0 squared over 2. Therefore, you get 1. Okay, so that's the value of that limit. You can tell that by looking at the graph. Second thing you do is do this limit. So we're going to do the limit of h of x. So the limit of 1, so what's the limit of 1? The limit of a constant is just the value itself, so that's equal to 1. So here's the thing, since they're both the same, okay, you kind of write this on the squeezing theorem, you could say this like this. You could say since the limit of the first function, f of x, is equal to 1, and the limit of the outer function, h of x, is equal to 1, then you could say that the limit of g of x, the cosine, is also equal to 1. And then you just say by the squeezing theorem. Okay, that's kind of the way that you would write your work out on that. That's kind of, so what you're essentially doing is doing the limit of f of x, the limit of h of x, those are the outer functions, and then the cosine's in the middle. So once you show that the limit of f of x and h of x are the same, then you can make that conclusion. So that's how the squeezing theorem works. And the importance probably for this level of class, there's probably going to be some things some formulas we have to derive with the squeezing theorem a little bit later on. Okay, so let's move to the next one, and I'm going to let you just kind of try this one on your own. Same idea, give you an inequality. You want to graph the three functions on your graphing calculator and then see if you can write this out kind of the way I did the last one. What I'm going to do is I'm going to start by just writing down f of x is 1 minus x squared over 6, which is a quadratic function. G of x will be the one sandwiched in the middle. So that is sine x over x, and then h of x is equal to 1. Okay, so just do a graph, and then use the squeezing theorem to find the limit of sine x over x as x goes to 0. Okay, it's a very similar example. So I'm going to pause video, you do the same thing, and kind of see what you get. Okay, so here's what, what you should have come up with. And this works exactly like the other example I gave you. So graphing calculator, you put this in. Really, you can use the same viewing window we did. So I just put in the three functions, 1 minus x squared over 6, sine x over x, and 1. Same viewing window. I just kind of cheated here, and I just used my calculator, and I just, instead of sketching the graph, I just did this, okay? So you want to make sure you have a graph that kind of looks something like that. And then the squeezing theorem, what you apply is you just do the limit of this. You want to do the limit of f of x, and then you want to do the limit of 1. And then you make a conclusion about the limit of the function sandwiched in the middle. So the limit of 1 minus x squared over 6 as x approaches 0 is 1. The limit of 1 is also 1, so then you can conclude that the limit of sine x over x is also equal to 1. But you just state that that's by the squeezing theorem. One thing I realized, and I kind of laughed about this a little bit, I don't know what I was thinking, but on the previous example I said by the SQ. The squeezing Q. I don't know what I meant by that. So I think that was intended to be squeezing theorem. Okay, abbreviation for that. Okay, so that's it. You won't do too much with the squeezing theorem, but actually it's going to turn out in this class that this limit right here is a real important limit when we start talking about derivatives of trigonometric functions. This is a limit that we'll come back to a little bit later in the class. All right, so the next thing I want to go to is I want to show you something that's kind of, I think is kind of interesting in theoretical physics and relativity theory, Einstein's theory of relativity. I'm going to talk about this example right here. I've even got a little video that I'm going to run through the end of this video, so I'm embedding a video in a video. That's real high tech. That if, in case you're interested in kind of getting a good idea what this is talking about. So the idea with this is you have a spaceship, and the length of that spaceship is L0. That's the actual at-rest perceived length of that spaceship that we would just measure and everything. It travels at a high speed, v, that's relative to the observer, and the ship is going to appear to have a smaller length than the astronaut on the spaceship by the Lorentz contraction formula. So not only does time slow down as your velocity speeds up in relativity theory, but also the perceived length of an object appears to contract. So if you see like a spaceship traveling real fast, if you could do that, it would appear that that length is really less than it really is when it's at rest. So your perception of the length would be different than the perception of the astronaut. So this is the Lorentz contraction formula. If you go a little higher in math, up into differential equations and stuff like that, you learn about Lorentz transformation equations, and that has a really big, is really big into the theory of relativity, the mathematics that Einstein developed in his theory. So what we're going to do is, what is the observed length of the ship if it's traveling at 50% of the speed of light? Okay, so let's go ahead and let's take a look at this. And in this part A, I'll show you kind of what we're going to do on this. So let's start by writing down the Lorentz contraction formula. L equals L naught, 1 minus v squared over c squared. Okay, like this. And what we're going to do is, it says that we're traveling 50% the speed of light. Now, c is the speed of light. Okay, and in this formula, it doesn't matter that you know what that is, so actually, you may know this from Einstein's probably most famous equation, E equals mc squared, where m is the mass and c is the speed of light. So what you would do in this case is you would do this. Okay, we're going to do this. We're going to do a simple substitution. So v is going to be 50% the speed of light. So it's just 0.5 c, and then we're going to plug that in like that, and we're going to work out what we get. Okay, so we're going to get L naught, which is the astronaut's perceived length of the ship. Okay, like this, and then what we're going to do is just do this replacement. So we have 1 minus 0.5 c, and then we have to square that whole thing, see? And then it's over c squared. So again, we just replace that with 0.50 c, then square it. So then what we have is L naught times the square root of 1 minus 0.25 c squared. When you square that 0.5 over c squared over c squared is 1, so you can remove that. And you end up having L naught, excuse me, and then 1 minus 0.25. So you get L naught times the square root of 0.75. And then we'll just do that on the calculator, and this will kind of give us an idea of how much the spaceship appears to contract. So, okay, so if I just do square root 0.75, work that out, I'll get this. So that is about 0.87 L naught. So that thing, if you think about this, what this means is that just means that the ship appears to be you could think about 87% of its original length, of the actual length that we measure if that spaceship was at rest. Okay, so that's the idea. Okay, so that's how that goes. Now let's move on to this next part. The next part is, very similar. We're just going to move on to 75% the speed of light. We're going to kind of see what happens to this perceived length of the ship as we increase our speed and get closer to the speed of light. So what we do here is we do L naught equals, or L is equal to L naught, and then we're just going to do something real simple here. We're going to replace this with 0.75 c, and then that's going to be over c squared like that. So we're just letting v be 75, excuse me, the percent of light, the speed of light. Okay, so this would end up giving L equals L naught. Then we have 1 minus, and then you could square this. You'd have to square this, and a kind of similar result will happen. So we take the 0.75 and square that. And I'll give this, so we get minus 0.5625 c squared over c squared like that. All right, and again, the c squared crosses out. So you're going to have L naught. And then we just do this. We do 1 minus 0.5625. So we end up getting this as the square root of 0.4375, like that. And then we'll do that on the calculator. So I just square root 0.4375, and that'll give this. So that gives about 0.66 of L naught. Okay? All right, so next thing we have is, I want you to kind of see what's going on this. What's happening is that square root's getting smaller and smaller. So as we go faster, what does it look like's happening? Yeah, the faster we go, it looks like that the ship is going to perceive to just get shorter and shorter and shorter. So it's going to be contracting. So that's kind of what we're talking about in part C. So as V increases, then the length appears to get shorter. All right, and then we're going to do this limit. So, calculus plays a big role in relativity theory in the mathematics. So what we're ultimately going to do on this problem is we're going to do the limit as v approaches the speed of light from the left-hand side of this Lorentz contraction formula. And then we're going to go ahead and just kind of work that out down. Okay, so that would be the idea of what we're going to do. A couple of notes I want to make on here. I'm kind of curious if you understand why this would have to be a left-hand limit. Okay, well, Einstein's theory says that in space-time, no object can travel faster than the speed of light. C is the speed of light, so that's why we're coming from the left. So the spaceship can't reach the speed of light. It can just get closer and closer to it. You can think of that kind of like how an asymptote works there. So essentially what we're going to do on this then is, well, you're just going to evaluate. You're just going to plug the C in. And what you would end up having is you would have L naught over 1 minus, replace V with C, so you would get really just C squared over C squared. That would cancel. So you're left with L naught square root of 1 minus 1. So that's L naught times 0. So it looks like that approaches 0, see? Okay? So it looks like as you get closer and closer to the speed of light, then the object, it could be a big spaceship, it could be the Star Trek Enterprise, it would just appear to shrink to nothing. It wouldn't, of course, but it would appear to. From the observer that's not on the spaceship. Okay, so that's how that goes, all right? That's kind of real interesting. Hope you enjoyed that. As something a little different. Now, I'm going to close off the video. This is optional, but you might be interested in this short video clip. And I'm going to open up. I'm just going to run this, and this will explain the Lorentz contraction formula pretty well, I think.
We live in the digital age. Smartphones, smart cars, smart houses.
Professor Dave again. Let's talk about length contraction.
He knows a lot about the science stuff. Professor Dave explains.
Einstein's special relativity was a huge step in physics. And even though time dilation seems like the weirdest thing you've ever heard, there's plenty more to get through with this theory. As it happens, it's not just time that's relative, it's length as well. And as we will find out, the math tells us that when you approach the speed of light, your measurement of space changes just like time. This is because if an observer on Earth and an observer in a fast spaceship register different spans of time for an event, they must also be recording different distances, since both observers agree on the same relative velocity between them. Specifically, the faster you go, the smaller objects seem to be, and the shorter the distance you perceive yourself to be traveling. This is a phenomenon called length contraction. Here we can see two versions of a spaceship traveling very fast to a faraway celestial object. In one, we see things from the perspective of an observer on Earth, and in the other, we see things from the perspective of someone on board the spaceship. The Earth-bound observer sees the spaceship moving at some velocity v, notices time moving at the familiar rate, and can measure some distance for the journey, which we label as L0 and refer to as the proper length, as this is the length that is measured by an observer that is at rest with respect to the objects demarcating the distance. But on the spaceship, the only thing that is the same is the relative velocity v, though in this case it represents the velocity of Earth and the destination as they move relative to the ship. And because this velocity must be the same as for the Earth-bound observer, everything else must be different. Because of time dilation, the time interval will be different, delta t0 rather than delta t. And we label the contracted length of the journey as L. The relationship between L0 and L is given by this equation, which can be derived from the time dilation equation. Not only do the two observers arrive at different values for the length of the journey, they even arrive at different values for the length of the spaceship, as this dimension is parallel to the direction of travel. The Earth-bound observer would see the ship as being much shorter than the astronaut does. In fact, this discrepancy in length neatly explains how the two observers could perceive different rates for the passage of time. It also explains how fast-moving particles can defy certain expectations, because at such speeds, time slows down, and the distance traveled contracts. So, a particle like a muon, with a half-life of a millionth of a second at rest, is able to exist for longer and travel further than expected when moving near the speed of light, due to relativistic effects. At this point, let's take a moment to make sure we understand how to assign delta t and L values. Delta t0 is the proper time interval, which is the time interval as measured by the inertial reference frame where the two events occur in the same location. For a space journey, that's the spaceship, because the Earth leaves and the destination arrives while the ship goes nowhere. Everyone else, like someone on Earth, will register a longer time interval, delta t, for this journey. L0, the proper length, however, is length as measured by an observer that is at rest with respect to the objects in question, like the Earth-bound observer is in this case. Anyone in motion with respect to the objects, like the person on the spaceship, will register some shorter length for this distance, L. This means that the proper time and length may not always be measured by the same observer, and we need to know how to assign these in order to do the math correctly. Let's say a ship is traveling from Earth to another system at 90% light speed. The person on board measures the journey as being 8.2 light years in length. How far away is the destination according to someone on Earth? Well, we can plug in 8.2 for L and 0.9 c for V. Then we just do some algebra and we should get 18.8 for L0, or the proper length between Earth and the destination. We still have more to go with special relativity, but first, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.